The lowest density PMI foam does not necessarily produce the lightest accepted UAV structure. A core may look favorable on a datasheet, yet add weight through resin uptake, extra reinforcement, oversized potted zones, rework, or rejected parts. The real selection target is a sandwich panel that carries its loads, survives the intended cure cycle, and remains within a repeatable finished mass range. Density selection begins with the complete structure, not the dry core. Skins carry much of the bending load, while the core separates those skins and transfers shear. Panel span, curvature, support conditions, aerodynamic loading, impact exposure, and allowable deflection all influence the required core performance. Compression, shear, tensile, and sandwich-flexure evidence can identify a candidate range, but individual material properties cannot qualify the panel by themselves. Skin thickness, fiber orientation, resin content, bondline quality, and edge treatment alter how loads move through the assembly. Flat coupons are useful, but representative parts are also essential. Curvature, cutouts, transitions, and hard points can create stress concentrations that never appear in a simple test panel. Local interfaces often govern the decision. Battery restraints, payload mounts, landing gear attachments, hinges, antenna brackets, and service panel fasteners introduce concentrated loads and compression zones. Instead of increasing density across the entire structure, engineers can use higher density material, inserts, or potted regions only where necessary. A mixed-density architecture preserves lower mass across lightly loaded areas while supporting demanding load paths. That efficiency depends on execution. Density transitions require controlled machining, clear material identification, accurate nesting, reliable bond continuity, and shop floor traceability. Without those controls, mixed grades can create assembly errors, excessive offcuts, or new stress concentrations. Manufacturing conditions are equally important. 3 variables deserve particular attention: resin uptake, cure cycle compatibility, and core conversion. During vacuum infusion, VARI or RTM, machined and exposed cells can absorb resin, changing both total mass and part-to-part variation. Actual uptake depends on resin viscosity, reinforcement architecture, temperature, vacuum integrity, flow path, surface preparation, and geometry. Any claim of reduced resin absorption should therefore be treated as a trial hypothesis. Verification requires matched panels made with the intended fabric, resin, vacuum level, and cure cycle. Thermal capability must also be evaluated as a complete process window. A maximum temperature rating alone does not qualify a foam for production. Pressure ramps, dwell time, thermal gradients, tooling expansion, resin exotherm, and the behavior of the bonded assembly can all affect dimensional stability and bond performance. Grade-specific guidance should be compared with the qualified shop procedure, then confirmed through a representative thermal cycle. CNC machining, thermoforming, and pre-shape delivery can reduce trimming and improve fit, but only when geometry, tolerance, packaging, inspection, and revision control are mature. Damaged edges or obsolete preforms can eliminate any expected savings. A disciplined decision can be organized around 5 weighted checks. Structural load carries 30%, covering compression, shear, bending, and local interfaces. Finished part mass carries 25%, including dry mass, resin uptake, trimming, and variation. Process compatibility carries 20%. Geometry and conversion account for 15%. Evidence and traceability complete the assessment at 10%. Before samples arrive, define acceptance bands for mass, deflection, local load response, dimensions, and repeatability. Then build representative panels and record dry core mass, reinforcement mass, resin issued, cure route, final mass, bond observations, and dimensional results. The defensible choice is not the foam that is universally lightest or strongest. It is the density or combination of densities that repeatedly produces an accepted UAV structure with controlled mass, adequate local performance, verified process compatibility, and a traceable reason for approval.